Hey, good morning, all you MRWC fans. We're here in Activity 7A4. Well, we're prepping for Activity 7A4 here in MRWC 2021. Oh yeah, during the crazy pandemic time. So I will develop this here for you guys and help you guys out, prepare for this activity. And there's a lot involved in this activity. It's actually quite cool. We're going to be using Desmos here for our activity, and what we want to do is learn about which function or when does a function have a hole versus an asymptote, and where does a hole occur, where does the asymptote occur based upon its domain, and can you predict whether an equation or a function here will have a hole or an asymptote. So how do you do that? All right, so what we're going to do is we're going to use a technology tool like Desmos here. You can use GeoGebra or any graphical program that you like, but I'm going to use Desmos to do all the work here, okay? And what we want to do is we want to use Desmos and also factor and simplify these functions to determine when and where it has a hole versus an asymptote. So we want to do the following things. So number one, we're going to use Desmos to graph each function. So we got to get prepared for that. Okay, secondly, we need to factor and simplify each function. And again, write this stuff at the very top of your lesson here, or your notes. So we want to factor and simplify each function, which we just call f of x in general. Okay, and then not number four, number three. How about number three? Number three, we want to generalize, when does it have a hole versus what's called an asymptote. All right, based upon what's going on. So what we want to do is generalize after we look at each function, simplify and factor and simplify each function, and also combine that with the use of Desmos. We want to generalize when a function, f of x in general, will have a hole versus an asymptote. Okay, and so yeah, we have a lot to do, and so what we need to do is get Desmos started here. Okay, so when you open up Desmos, this is what you see. These are the default functions here. You want to clear them out, of course, and because these are obviously different functions, and you want to put a title in the graph and put in 7A4 prep and activity. Type that in. Okay, and you can save your work as you go. Okay, now I've already done this. I've already entered in all the functions, and you, okay, obviously you need to do the same thing. And I'll show you what's going on throughout the activity by plotting the functions in Desmos and learning from the results. Okay, so that's the plan. And so obviously this is a video, so go at your own speed, save your work as you go in Desmos here. Just hit the save button and record all your functions, okay, because you're going to be submitting this with all your notes and everything. So get involved and get really good at Desmos. This is free and available to anybody. Okay, anybody. Is available on the iPad, any kind of iPad, tablet device, phone, any kind of phone, and any computer, Mac or PC, it doesn't matter. So let's use Desmos here, record your work, log in, and sign into your account so you can save your work. All right, so here we go. First of all, let's take a look at this function here. We got h of x here. When you put this in Desmos, you just type in y. Y is the same thing as f of x or h of x. Okay, so these are just y, another name, or what's called function notation for y. So when it says h of x, you're thinking y is equal to the quantity of x plus 3 times quantity of x minus 2 divided by x minus 2. Does this function have a hole or an asymptote at 2? Okay, because all of these functions, if you look at them all the denominator is x minus 2. That should be obvious. And so because of that, the domain for all of these functions is all reals except 2. In fact, let's write that down at the very top. So for all of these functions, the domain is all reals except 2. Except x equals 2. Okay, so you can say x not equal to 2. Okay, so anything but 2, because as you guys know, you can't divide by 0. And in the denominator here, if you plug in 2 or substitute in 2, Well, 2 minus 2 is 0 and it blows up, okay? And you do not have a defined function at 2. So what happens? Well, you have two options, okay? There are only two options. All right, option 1 is, do you have an asymptote at 2? Option 2, okay, do you have a hole at that point? And if that's the case, if you do have a hole at that point, where is it located at? So you can figure out all that information. So what you want to do is factor and simplify each one of these functions, graph each one in Desmos, and learn from Desmos which one has a hole and which one has an asymptote. It's that simple. Now, this one's already factored. So let's just take a look at it. Let's put it in Desmos. And you can see here, just by looking at the graph, I'm going to zoom out here, you have a line, okay? A line. Why is it a line? Why is that? If you look at it right here, the y-intercept is at, let's look at it. Okay, well, it's at 0, 3. And the slope looks like up 1, right 1, up 1, right 1. So it's a slope of 1. So this looks like y equals x plus 3. It's a line. But if you're looking a little bit closer right here, look at maybe where x is 2. Let's see if I can get it at 2 here. Okay, you'll notice, right there, okay, you see that? 2, it's undefined. Why? Because you can't divide by 0. The domain of all these functions is all reals except 2. It can be anything other than 2 because you cannot divide by 0. Okay, so, but at 2, at x equals 2, do you have a hole or an asymptote? And clearly this line, this linear function right here, does not have a asymptote because this is not asymptotic to any value, okay, or to any line. But it does have a hole. Look at that. It has a hole at 2, 5. So why? So what we want to do is factor and simplify. Now this one's already factored. So if you simplify that, x minus 2 divided by x minus 2 is 1. And that gives you a new function. Okay, it looks like h of x is equal to x plus 3. Holy cow, that's the same thing as y equals x plus 3. All right, and this is a linear function. As I said, the function here, linear function here, has a y-intercept of 3. Notice that here, this is y equals mx plus b, y equals mx plus b. Notice the y-intercept is 3, and the slope is 1, which corresponds to the graph here. But it doesn't have an asymptote, it has a hole. So let's write that down. It has a hole at 2 something. Now going back up here to the graph, if you go back to 2 and figure out where it's undefined at. So it's undefined at 2, but if it's undefined at 2, that hole is at 2, 5. And why is it 5? Well, if you plug in 2 into the linear function, okay, f of 2, not the original function, the linear function here, not f, h, I'm sorry. Let me write h. 2 plus 3 is obviously 5. So it has a hole at 2, 5. Okay, so notice that we removed the discontinuity right here. This is called a removable discontinuity. And we ended up having a hole and not an asymptote. So no horizontal asymptote. Vertical asymptote, sorry. No vertical asymptote. Okay, we have a hole at that. And the way you find the hole is by taking your x value, all right, and substituting into the simplified function, which is x plus 3. 2 plus 3 is obviously 5. So you have a hole at 2, 5. And when you're able to cancel and simplify like that, you end up having a hole. Now, does that happen every time? And that's what you have to learn in this activity. Does every time you cancel out a term like that, does it give you a hole and not an asymptote? Well, to answer that question, you got to do a lot of research. So that's why we have 6 functions and not only 1. Okay, so this right here, when you remove the discontinuity, it's called a discontinuity because there's a hole there. It's not continuous there. You call it a removable discontinuity. Okay, so at x equals 2, you have what's called a removable discontinuity. You should have learned about this in Algebra 2. Discontinuity. However, if you don't remember it, okay, now I've just enlightened you on what it's called. Okay, so holes are called removable discontinuities because I removed it by simplifying. I came up with a linear function right here, okay, which is y equals x plus 3. And we have a hole instead of an asymptote. Okay, number 2. So let's deselect this one, and here's number 2. Now number 2 is clearly different here. So check out the graph. It's this really crazy looking graph right here. And notice that it's asymptotic to some vertical line here going up, and on the left-hand portion of it, it's asymptotic to some vertical line down here. So let's zoom out, or zoom in actually. And I want to type in x equals 2 here. Make sure you do the same thing, because it's not continuous at 2, because obviously it has 2 pieces here. So at 2, it behaves asymptotic to line x equals 2 on from the left, and as you get closer and closer to that vertical line, it goes down to negative infinity. From the right hand side of 2, it goes up towards positive infinity. So in this case, this function does not have a hole, it has an asymptote at x equals 2. Okay, so let's write that down. So it has a vertical asymptote, VA is vertical asymptote, okay, at x equals 2. You can see that in the green function on the right here, and there's no hole. Okay, the previous function had a hole, but this one has a vertical asymptote. So why is that? Well, let's factor it. Okay, we haven't done step 2, factor and simplify. So let's factor k of x. That's how you say it, k of x. Now the numerator is a difference of squares, so you factor it as x plus 1 times x minus 1. Okay, it's called a difference of squares. And this is why we prepped you with factoring, because you have to know this basic stuff. We start learning this in Algebra 1, and by pre-calc, and this is a pre-calc course, you should know how to factor. So from here to here, we factor. All right, and we factor x squared minus 1 as x plus 1 times x minus 1 using structure, using the previous techniques. And we divide that by x minus 2. And notice that nothing cancels. Okay, nothing cancels. There's it's totally different than h of x, the first one. First one, the common factor of x minus 2 canceled. Here, nothing cancels. So nothing cancels, and the domain is all reals not equal to 2, and that means that we had a vertical asymptote. So does that imply that every time you have a function and there's no term that cancels, you cannot remove the vertical discontinuity? If you can't remove it, does that always imply that you have a vertical asymptote? And that's what you have to learn. It's like, does that imply that all the time, or does it not? In order to understand that, you got to do multiple examples, right? As we always do. So let's investigate further. Okay, so let's take a look at this one here, number 3. So I'm going to deselect the number 2, and let's put in number 3. So type that in if you haven't done so. Like I said, I've already typed these in, and that's what you guys have to do. You have to type the functions in. It's not that hard to do. You just type it in, and then you take a look at the graph. And notice that we have a linear function again. Holy cow. Is it defined at 2? So let's scroll along the graph. Just grab a point on the graph and use your cursor and scroll and go into 2. And notice that at 2 it's undefined. Do you see that? Right there. It's undefined. So there's a hole at 2 again, at 2 comma 1 in fact. Okay, it's right 2 up 1. So the hole is at 2 comma 1. Why is that? Well, let's factor and simplify. Okay, so here we go. So f of x is equal to, and then this is, let's factor this trinomial here. And again, this is why you have to be good at factoring. So go off to the side and use whatever technique you want. But when you factor this polynomial, you'll get x minus 2 times x minus 1. Okay? So what I just did there is I took the numerator and I just factored it. Okay? And that's what you have to be good at. That's why there was a prep before this on remembering and being really good at factoring, because guess what? You need to. All right, that's how you determine whether it has a hole or an asymptote. So notice here there's an x minus 2 in common. So if we factor it at first, like we did, simplify, anything divided by itself is 1. All right, we get this new function f of x. This is the simplified function. That's equal to x minus 1, which is a linear function. So your y-intercept is negative 1. So look right here on the graph, it's 0, negative 1. That's your y-intercept. The slope is 1. It goes up 1, right 1, up 1, right 1. Okay, so this graph makes sense because it's a linear function. But it's got a hole at this point right here at, let me see, try this if I can get it here. It's kind of hard to do. There you go. At 2 comma 1. So how do you know that? So So whole at 2 comma what? Well, you find f of 2. You put 2 in the function, not in the original function, in the new simplified function. And, 2 minus 1 is 1, so f of 2 is 1. So it's got a hole at 2 comma 1. All right, as seen in Desmos. So once again, number 1 and number 3 are very similar because we were able to remove the discontinuity and we had a hole. So it's called a removable discontinuity. Got to get used to this lingo here. Anytime you can remove it by simplifying, it's called a removable discontinuity. Discontinuity means that it's where the function breaks. Okay, there's a gap in the function, whether it's an asymptote or a hole. Okay, it's discontinuous there. You'd have to, if you were tracing the function with your pencil, you would have to lift up your pencil and then move on to the next portion. Anytime that happens, you have what's called a discontinuous function. Now, how about functions? The next functions. So let's analyze them. So let's put in function number 4, g of x here. So and type it in. And again, if you're working with me here online and you haven't typed in the functions here, obviously pause and play and rewind as much as you need to. But you have to do it yourself. So pause the video, get those functions in, and then obviously hit save periodically on Desmos so you can save your work. Okay. So notice that we got to type in x equals 2. That's the green line here. And notice on the right side of 2, as you approach 2 from the right, it goes up to positive infinity. And on the other side, if you approach 2 on the left side, it goes down to negative infinity here. Okay, so we have a vertical asymptote, but why? Okay, so let's factor. So g of x now is going to be equal to something here. So two numbers that multiply to 2 and add to 3 are 1 and 2. So it's x plus 1 times x plus 2. And notice that nothing cancels again. I mean, x plus 1 is different than x minus 2, and x plus 2 is different than x minus 2, so nothing cancels. Okay, no removable discontinuity. No removable discontinuity. Okay, you can't remove it. Because of that, we don't have a hole. So no hole. Okay, that means we have a vertical asymptote at x equals 2. As seen in the graph right here. So if you look at the function here, it's asymptotic on the right side going up. It's asymptotic on the left side going down to negative infinity. So that's how you tell, guys. If there's no removable discontinuity, you have an asymptote. If you can remove it, you got a hole. It's that simple. But the key in this is that you have to factor. So now let's move on to h of x. Okay, let's get this guy. Let's factor this. Now, actually, let me show the graph first. So let's type in the next one here. So here's the graph. And it's clearly not asymptotic to this green line, so deselect that. It's a linear function again. Holy cow. Okay. And look at this. Why does it has a, let me see. It has a y-intercept of 1, and it has a slope of 3. Okay. It goes up 3, right 1. So it must be 3x minus, or 3x plus 1. So how does that happen? Why is this linear? And let me see at 2. Let's go up to 2, right there. Let me see if I can get it right at 2. There we go, right there. It's kind of hard. It's hard to, but it's undefined at 2, and it's at undefined at. There's a hole at 2 comma 7. Okay, so how do we get that? So let me see. 3. I'm going to use FOIL. 3x times x is 3x squared, and the factors of 2 are 1 and 2, and they need a negative in the middle and negative 5x. So I'm going to make that negative and that positive. So it's 3x plus 1 times x minus 2. Let me rewrite that. 3x plus 1. So 3x plus 1 times x minus 2. Now notice that the x minus 2's cancel. Look at that. And I get a new function. All right. It's simplified function. H of x is equal to 3x plus 1. So again, this is the same thing as a linear function y equals mx plus b. So the slope is 3 and the y-intercept is 1, which corresponds to everything I just said on the graph. It's up 3, right 1. Up 3, right 1. So, because of this, we have a hole, okay, at x equals 2. So what is the hole? Well, it's 2 comma something. And so you want to plug in 2. So 3 times 2 is 6, plus 1 is 7. So the hole's at 2 comma 7. Okay? 2 comma 7. The reason why is because you were able to remove the discontinuity. And when you do that, you switch from an asymptote to a hole. Okay? And that always happens. All right, number 6. Number 6. Here we go. We have to factor. Well, actually, let's take a look at it. So let's type that in. So type in the function there. Holy cow, look at this. Let's put in the vertical asymptote at x equals 2. And notice that it's asymptotic going up. And if you go down, not asymptotic to that. But at least it's asymptotic on the left side going up. All right, so this is a weird function here. So is there another piece to it? I don't know. Let's see. So what is that? Okay. Ooh, it's not asymptotic. Look at this. What happened here? So let me see. We have... Oh, it must have a hole. Must have a hole. It's not asymptotic, but there must be a hole at 2. So let me get a little closer here. Let me go up the function here. Okay, so I misstated in the very beginning. So let's go to 2 here, and it should be undefined. Boom, right there. Okay, see that? Right there. Okay, so it's undefined at 2. So it's not. There's no asymptote here. There's only a hole. Okay, so why? So let's factor. Okay, that's the key. That's why I said at the very top, right here, you have to use Desmos to learn from it. There was no asymptote here. Initially it did, but when I expanded it, okay, and I looked at a bigger portion of the graph, obviously the graph crosses the vertical line, so it's not asymptotic to that line, okay, but there's a hole at 2. But you know why? Okay, where? So let's do this. Let's factor. So let's get k of x here. Okay, and there's a common factor of x, so let's factor it out. Oops, didn't do that right. So factor out the x, you get x times x cubed minus 8. And by the way, 8, as we talked about in our previous activity, that's 2 cubed. So this is a difference of cubes, guys. So difference of cubes, you can refer back to your factoring exercise in the preceding lesson that you went through. This is why I did it, because it comes up. And you got to factor that baby. All right, so let's factor it. So bring down the x here. And then the bases are x and 2, because 8 is 2 cubed. So you go x minus 2 times, and you square the first, change the sign, multiply, square the last. And then you divide that by x minus 2. This is your new k of x. Okay, now check this out. They have a common factor, so you simplify it, right? And you get k of x is equal to x times this trinomial, x squared plus 2x plus 4, which is just a cubic. When you distribute through the x, okay, you get x cubed plus 2x squared plus 4x. It's a cubic. And you guys learned about cubic polynomials in Algebra 2. They have this shape right here. This very famous shape, all right? And they have no asymptotes, and they're continuous functions, but it's discontinuous at 2. So there's a hole, in this case, at 2 comma something, well, not x, but 2, at 2 comma something. So you have to substitute in 2 and evaluate it. You got to find k of 2. So I'm talking about using this new function here, not the original, but the new function. So you got to figure out what 2 cubed plus 2 times 2 squared plus 4 times 2 is. So I guess we better do that. So 2 cubed plus 2 times 2 squared plus 4 times 2. So that's 8 plus 2 times 4 is 8 plus 8, that's 24. Okay, so let's see if we have that. So let's zoom, let's go to the graph here so we can see this a little bit better here. And we need to figure out this point right here. So it occurs right about here. So notice the scale is by 2s, 20, 22, 24, 26, 28, 30, okay? And we're at 2 units high on the graph, but the scale is 2, so that's at 24. So the result makes sense. All right, so it's 2 comma 24. So right there, I know that the function has no vertical asymptote because it was not asymptotic, it was clear. And then, but it does have a hole, a break in the function, all right, and it's discontinuous at 2 comma 24. Okay, yeah, I told you this is there's a lot, okay, and that's why I'm making a video on this so you guys can go at your own pace. All right, because this is a very abstract, complicated subject. It requires a lot of algebraic skill like factoring, and then you have to learn from Desmos, and you have to be good at Desmos, right? You have to know how to enter a function in. Okay, now let's go to the next discussion piece. All right, what do you notice about the function values? Function values are y values. You have to know that. So make a note of that in red. When I say function values, I'm talking about the y values of the two functions. Okay, f of x equals x squared minus 4 divided by x minus 2, which is, let's see here, this one. Okay, so there's that function. Type that in Desmos, and g of x, which is 1 divided by x minus 2. Okay, so that's this one. So we're going to analyze these functions. So type them into Desmos, pause, type them into Desmos, and then press play when you're ready. And let's figure out, you know, what happens to these functions in the immediate neighborhood, new terminology here, immediate neighborhood of x equals 2. When I say immediate neighborhood, I'm talking about when you get really, really close to 2. Okay, when you get close to 2, from the left and from the right. All right, describe and compare the behavior of the functions, behavior of the function values, behavior of the function values. We're talking about the y values again. All right, do they approach something, or do they go to infinity, or do they go to negative infinity? You know, what happens? So as you approach 2 from the left or the right, what happens to the y values when you do that? Well, let's figure that out. All right, so we graph them. So let's graph them one at a time. So type in the first one here, and let's analyze it. Okay, and notice it looks like a linear function again. So it looks like a linear function, but it's not defined at 2, so there's a hole at 2. Okay, so if you go to 2 right here, you'll notice that it's undefined right there. See that? It's undefined. So the domain for both of these functions is all reals except 2, just like the previous graphs. All right, let me capture this function here and just take a look at the graph. Just so I can annotate. Okay, so there's your first function, that's f of x. And we are obviously not defined at 2 here, so it's all reals except 2. And there's a hole there, so let's annotate a little bit here. So here's 2, and you got to go up to the graph, okay, and put a hole there at 2 comma 4. So this hole there at 2 comma 4. Okay, but why, you know, what's the behavior, what's happening to the y values when you approach 2 from the left? And what do the y values approach? When you approach 2 from the right, what do the y values approach? So here's how you do it. So when you approach 2 from, as x approaches 2 from the left, the way you write that is as x approaches. So draw an arrow, that means approaches. 2 from the left. Now when the symbol from on the left is this minus sign. That means from the left. Okay? This is all symbolically now. So as you approach 2 from the left, what are the y values doing? Well, when you're approaching 2 from the left, let me do it on the screen here first. Take a look at that. Put your cursor on the screen here or on the graph, and as you approach 2 from the left-hand side, the y values are getting higher, higher, and higher, and higher, and they're getting closer and closer to, boom, 4. They're getting approaching to 4. All right, so you're going this way on the graph. So as you go, as x approaches 2 from the left, the y values get bigger and bigger and bigger, and guess what? The y values approach 4. So you say y approaches 4. approaches. Remember that arrow is a new symbol. Let me write it down somewhere. So this new symbol, the arrow symbol, means approaches. Okay, so write that down. Now, if you approach 2 from the right, something different happens. So if you're coming in from the right side, as x approaches 2 from the right, okay, now the symbol for that is different. You got a plus sign. This means from the right. From the right. So as you approach 2 from the right, what are the y values doing? Well, you're cruising down this way on the function. All right, and the y values are getting smaller, 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 and they're decreasing up until this point at 4. Okay, so y approaches 4 if you come in from the right. So this is what we say about describe and compare the behavior of the function values. Function values meaning y values. Where do they approach? And if they approach something, what is it? Okay, and if it doesn't approach anything, then it's probably going to be either positive or negative infinity. Now, to see that numerically, what we're going to do is create a table, which I did right here. So I'm going to redo it here. So what we're going to do is take this function, hit the gear symbol. All right, I want to duplicate this function first. So hit the duplicate symbol. And then what I want to do is, for that function here, I want to change it to a table of values so I can see some values. All right, the y values. Now this is cool, so check this out. We want to figure out what happens when you approach 2 from the left. So we got to get really, really close to 2. Okay, so notice that it says at 2 it's undefined. So come up here to the top here, and let's change the values. Let's say you're at 1.9. Okay, that's pretty close to 2. So look right here. You'll notice that the y value is 3.9. Well, let's get a little closer than that. Let's go down here, clear out this one. Let's type in 1.99. Okay, notice the function value, the y value is 3.99, which is very close to 4. Okay, as I said over here on the left. All right, let's get even closer than that. Okay, type in 1.999. 1, 2, 3. All right, and notice that the y value is 3.9999, which rounds to 4. Okay, but let's get even closer than that. 1.9999. And notice that we get even closer to 4. So as x approaches 2 from the left, as you get really super close to 2, all right, the y value is getting closer and closer to 4. This is the numerical approach of understanding what the function values are doing. Now at 2 it's undefined because you can't divide by 0, as we've been talking about. Now let's go on the right side. Let's enter in some values. Now let's enter in 2.00001. Okay, that's pretty darn close to 2. That's very, very close to 2. And notice that the y value is very close to 4. And let's move away. Okay, let's go farther away. So 2.0001. So I'm going further away. That's not as close as the previous one. And notice that the number is a little bit bigger. And let's go a little bit further away. 2.001. That's 2 and 1/1000ths. Okay, notice that the numbers are slightly bigger right there in the y values. And let's go a little bit further away, so 2.01. And notice that the number keeps increasing. So as you get further away from 2, the number gets bigger. Okay. Conversely, if you get closer to 2, the y values approach 4. Okay. So if you approach 4 if you get closer on the right side, the y values approach 4. You approach 2 on the left side, the y values approach 4. So on either side, they approach 4. That's basically what I'm saying. And this is the numerical approach to figure out what the function values are doing, when you're approaching a certain value from either left or from the right. Okay. So right here, let me just restate what I just stated here, since I have the values in here. So when you're from the left, this is from the left. Okay, you're approaching 4. This y approaches 4 from the left. As you're coming in from the right, this is from the right down here. because it's to the right of, all these values are to the right of 2. That's why it's from the right. The y values are also getting closer and closer to 4. All right. So on either side of the hole. Now what's happening on this other function? So let's type in g of x. So let's deselect these. Let's put in g of x. Now g of x has an asymptote. If you look here, it's asymptotic going up, it's asymptotic going down. Okay, and notice that it happens at this vertical line where as s equals 2. So I need that vertical line again. I'm going to bring this one down here so I can use it. Okay, I'm going to turn this vertical line on. So on this green vertical line, you can see how it's asymptotic going up to positive infinity. It's asymptotic going down to negative infinity. Okay, asymptotic to the line y equals, or x equals 2. So notice that. So let me grab this function here. There's a reason why that happens. Okay, so let me just bring in the function so we can take a look at it. Okay, give me a second here. Let me just reboot my program. There we go. Okay, give me a second. Let me just realign everything here. Technology is great, but you gotta learn how to use it all and make it work for you. Okay, so we got this function. There we go. All right, so when you're approaching 2 from the left hand side, so the function values, I'm going to use arrows here, they go down to negative infinity. So we can say from the left, as x approaches 2 from the left, y approaches not a specific value, it gets lower and lower and lower, and we say it approaches negative infinity. It gets more and more negative. Something different happens on the right. When you approach 2 from the right, the function values go up, 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 and away, as Buzz Lightyear used to say, to positive infinity. So we say as x approaches 2 from the right, the plus sign means to the right, y approaches positive infinity. So this right here, this is really different behavior than the previous one, and the reason why it has an asymptote is that you can't factor it. Okay, g of x is not factorable. There's no removable discontinuity. So for g of x right here, okay, no removable discontinuity. We have a vertical asymptote at x equals 2. Okay, no holes, but we have that vertical asymptote. And so notice that the function values, the y values, all right, they behave totally different as you approach 2 compared to the previous graph. Huge, huge difference there. Okay, and because the first one has a hole and the second one has an asymptote. Okay, so no hole here. All right, because there's no removable discontinuity. Okay, you can't simplify that function. All right. Yeah, I know, this is pretty intense stuff. So what we want to do is understand that a little bit better here. So on this next discussion piece right here, instead of giving you the function, I'm going to give you the graph and ask you the same basic questions to analyze the behavior of the function values around the indicated values. So in these 4 here, it says describe the behavior of the functions. Okay, these are the y values now. Behavior of the functions, that we're talking about the y values, around the indicated value. So on the first one here, we're talking about what happens when you approach -1. On the second one, same thing. What happens when you approach -1? On the third one, we want to figure out what happens at -3, but we also want to figure out what happens when you approach 1, because this one has 2 vertical asymptotes. And then on this fourth one here, what happens when you approach 1? So let's handle it one at a time. So on this one here, let's take a look at it here. So the key point in question is what happens to the function, this is f of x right here, what happens to the y values as you approach the function from the right, because it doesn't exist on the left. So f of x does not exist on the left side, exist on the left side of -1. Hopefully that's obvious. There's nothing there, guys. Okay, so you have to approach it from the right. Okay, so we're going to approach -1 from the right. As x approaches -1 on the right, what happens? Well, the function values, they get smaller and smaller and smaller, and if you just follow the function, it goes down to -infinity. So I can say very confidently that as x approaches -1 from the from the right, excuse me. So put a plus sign there. This means from the right. Okay, comma, y approaches -infinity. Y, these are the function values right here. Okay, so you have to understand what I mean by behavior of function values. I'm talking about the y values. So when you go from the right, and when you approach a next value from the right, the function values obviously go down to -infinity. Okay, what happens on the second graph? Okay, so this one has two asymptotes, a vertical and an oblique. Okay, so let's analyze from the left first. So if we come in from the left, okay, to -1. So as x approaches -1 from the left, again, this minus sign means left side. Okay, what happens? Well, you're down here on the function, so it goes down, these are arrows, okay, down, towards -infinity. So y approaches -infinity. Coming in from the right, something different happens. So when you're coming in from the right side, x coming from the right side, they go down, but then they go up, all right, to +infinity. So as x approaches -1 from the right side, that plus sign means right side, y approaches +infinity. They get infinitely big. They go up, 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 and away, like Buzz Lightyear used to say. Okay? All right, what happens in the next few graphs? So let's take a look at these guys. Okay, so what happens when you come in from the left? Okay, so as x approaches -3 from the left, okay, you're going up, 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 and away to +infinity. So y approaches +infinity, which just means it gets very, very big. Now from the right hand side of -3, okay, this is from the right, so as x approaches -3 from the right, so you use the plus sign there, all right, the function goes down, down, down to -infinity. So y approaches -infinity there. So you have to understand how to view it and how to see it. You have to understand how to go from the left and from the right. Now let's go to the right of from the left of -1. Excuse me, +1. So the second part, as x approaches 1 from the left, okay, coming in from the left of 1, left side. This is left side, obviously. The other side is the right side. The function values go up, up, and away to +infinity again. So y approaches +infinity. But if you come in from the right, this is obviously from the right side, the function values do the same thing. Okay, you're going to see functions actually do this. There are well-designed functions that do this. So as you approach 1 from the right side, plus sign, y goes to +infinity. So this is analyzing a function graphically, what happens to the function values as you approach a particular x value. So unlike in the last graph here, if you're coming in from the left, so left of 1, so as x approaches 1 from the left, where the y values approach? Well, they go down, 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 down to -infinity, all right? If you're coming in on the other side, from the right, it's obviously on the right side. What do they do? The function values go down, 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 down to -infinity again. So you say as x approaches 1 from the right, y approaches -infinity. Okay? So you need to represent what's going on using symbolic notation, using symbols for the left and for the right, or from the left and from the right. And that's what, and you have to determine when does a function have a hole versus an asymptote. That's what the initial part of this activity was all about. So in sum here, in summary, to determine whether a function has a hole or an asymptote, number one, you can use Desmos. Number two, you can use factoring and simplifying, and you should be able to determine whether it has a hole or an asymptote. Okay, and then of course you can use a table of values to also see what's going on as well, as I showed you. So you can duplicate a graph, convert it to a table, and enter the values in. So you need to be able to be skilled on that too, because activity 784 has you do that. So in 784, first thing is you got to fix, okay, these values here. These should be -1s. So change that to number 2. And then in number 1, you're going to be using words and symbols and write things symbolically to see what happens with the function values, the behavior of the functions, meaning y values. Again, behavior of the functions or y values at the indicated values, just like I did in the previous one here. You're going to do the same thing. And then number 2, you're going to do what I did in Desmos here, and you're going to approach the point of discontinuity, which in this case is -1. You know, the domains for all these functions are all reals except -1. And you're going to get really, really close to that point, that undefined point, from the left and from the right. So again, this is going to be from the left, and then this one here is going to be from the right. Okay, and you're going to use Desmos here, so let's make a little note of that. Number 2, you're going to use Desmos heavily. So number 2, use Desmos for your tables. Okay, and save all your work, and you're going to submit this. Okay, because this right here is how you're going to get all your function values. Doing this on a T84 is difficult. Trust me, I had my students try it on a T84, and they were making all kinds of mistakes. Desmos, piece of cake, because it does all the evaluation for you. Okay, so go ahead and work on that, and I will see you in my next activity. This is Mr. Ainsworth here on MRWC. Hopefully you learned something there, and I'll see you soon. Take care.